So in this video, we're going to talk about hashing. Okay, so a bucket is a unit of storage containing one or more entries. Okay, so it could have varying different sizes. Okay, and we can obtain the bucket of an entry using its search key value. Okay, so there's a hash function. Usually it's going to be a mod function. Okay, so hash function h is a function from the set of all search key values k to the set of all buckets addresses b. Okay, so in a hash index, buckets store entries with pointers of records. Okay, sometimes we can have a bucket of overflow. Well, a lot of times you're going to have overflow. Okay, so this is because of insufficient buckets, and there could also be a skew in distribution of records, meaning, you have records in the first half, a lot of the records from the first half of all the buckets. Okay, so it could be a skew. So we have multiple records that have the same search key value, okay, or we maybe have a bad hash function that produces non-uniform distribution of key values. Okay, so although the probability of bucket overflow can be reduced, it's not possible to eliminate it entirely. Okay, so it is handled by using overflow buckets. Okay, so we define M target addresses here. So each of these are buckets, okay, and each of these have different addresses. Okay, 0, 1, 2, all the way to m minus 1. Okay, so we create a hash function. Okay, this is a hash function, and this is defined for all possible values of the key k. Okay, so when you feed this key into this hash function, it's going to return an integer value h such that it's between 0 and m minus 1, and depending on that value, it's going to be placed in one of these buckets. Okay, and each of these buckets have multiple entries. Okay, so this is the basic idea. You feed in the key, okay, and then it's going to return an address to the bucket that it's supposed to go. Okay, so how do we handle overflow, bucket overflow? So we could do overflow chaining. So the overflow buckets of a given bucket are chained together in a linked list. So if you have taken database or data structures, I'm sure you all have, you know what a linked list is, right? So it looks something like this. Okay, so this is the original bucket, and then it has a linked list, and these are going to be called the overflow buckets for bucket 1. Okay, so this is also called closed addressing, open addressing, closed hashing, or open hashing, depending on which book you're using. Okay, so this is each of these buckets are containing records. So this one contains 1 record, this one has 2 records, and it's full, right? So now we have an overflow bucket, right, using a linked list, and now we are able to fit it in this overflow bucket. Okay, so we're assuming that each bucket contains 2 records. Okay, so if we were to add another record into this one, we could just fit it here, and then what if we would add another one? It's full, right? So we would have a linked list. Okay, so and then you could have another one and so on. Okay, so this is called overflow buckets. Okay, so a bucket can contain many more keys than records, right? So it's really important to find a good hash function, okay, which evenly distributes the records among these buckets. Okay, so the key here is numeric, so you want to divide the key by a number of buckets. So usually you use the mod function. Okay, so depending on how many number of buckets you have, you would use this mod function with that. Okay, so hash file organization of, let's say, instructor file using department name as the key. Okay, so there's going to be a figure in the next file. So let's say we have 10 buckets total. Okay. And the binary representation of the ith character assumes is to be integer I. Okay, so the hash function returns the sum of the binary representation of the character modulo 10. Okay, so if you feed music into, this is the department name, it's a key, right? So if you feed the key music into this hash function, it's going to return 1. Okay, so anything with key music department is going to go to the bucket number 1. Okay, what if history goes to bucket number 2, physics goes to 3, electrical engineering also goes to 3. So notice how these 2 keys have the same value for the hash function. So it's going to be going to the same buckets. Okay, so here is the example that we went over. So we have 10 buckets. Well, it's not showing the whole 10, but assuming there are 10. Okay, this is based on the key, which is our department name, right? So music goes to bucket 1. Okay, and then remember physics and electrical engineering both went to bucket 3, and so on. Okay, so you can kind of see an example of a hash file organization. Okay, so there's deficiencies of static hashing. Okay, so function H maps search key values into a fixed set of B bucket addresses, right? But databases grow and shrink all the time, right? So if the initial number of buckets is too small, we don't have enough number of buckets, then as the file grows, performance will degrade due to having too many overflows, right? If space is allocated for anticipated growth, then a significant amount of space will be wasted initially, right? So, if let's say you have 10 records, you don't want to just make, enough buckets for just 10 records. You want to make enough because you know that it's going to be growing. Okay, so initially it's going to waste some space, but eventually it's going to be filled, right? As if database shrinks, again, space will be wasted. Okay, so one solution is to reorganize all the files with hash functions periodically. Okay, but this could be expensive and it disrupts the normal operation. So a better solution is to allow the number of buckets to be modified dynamically. Okay, so what is dynamic hashing? So there are different types of dynamic hashing: periodic rehashing, linear, and extendable hashing, right? Periodic rehashing is if a number of entries in a hash table becomes, let's say, you could just pick a number, 1.5 times the size of the hash table, then you create a new hash table. Let's say you could pick a number here as well, 2 times the size of the previous hash table. Okay, so you can rehash all entries into the new table. Okay, so you're rehashing periodically whenever it reaches a certain, percentage. Linear hashing is you're doing rehashing in an incremental manner. Extendable hashing is tailored to be disk-based hashing. Okay, so with buckets shared by multiple hash values, you just double the number of entries for each hash table without doubling the number of buckets. So now each bucket is able to fit more. Okay, so comparing the ordered index and hashing, there's costs of periodic reorganization, which could be expensive. You have also the relative frequency of insertions and deletions. Okay, sometimes maybe certain databases you don't need to insert, and delete very often, right? Is it desirable to optimize average access time at the expense of worst case access time? Okay, so these are all things that you should consider picking between the ordered index and hashing. Okay. You could also have multiple key access, right? So here we have 2 keys. We have department name and salary, right? So we're selecting ID from instructor table where department name is finance and salary is 80,000. So it's possible strategies for processing queries on a single attribute. You could just do, you could have index on just department name to find all the instructions in the finance department, and then you can use test, okay, for the salary. Or you could have index on the salary, and then you could have test on department finance. Okay, or you could use department name index to find the pointers to all the records pertaining to the finance department. And similarly, you could do the same thing, have an index on salary, okay? And whatever was returned here and here, you just take the intersection of both of these sets. Okay, you could also have composite search keys. Okay, so let's say you have a search key on department name and salary. This is a composite search key. Okay, so for ordering, you're going to first check to see which of these the first value is larger, right? If this is larger, then obviously it doesn't matter what these values are. This is going to be larger in general. What if these values were the same? Then we go to the second one, A2 and B2, to see which one is larger, and then we pick. Okay, so we have indexes on multiple keys. Okay, so same thing here. Suppose we have an index on combined search key, department name and salary. Okay, so with the where clause, you could have where department name is finance and salary is 80,000. Okay, so the index on these can be used to fetch only records that satisfy both of these conditions. Okay, so this could also handle, so since 80,000, it's a number, right? So this could be handling equal to, less than or equal to, greater than all of those, but it's not as efficiently handling, finite, okay? Okay, because it's not a numerical value. Okay, so this is how you create an index. You use the keyword create index, and then this is going to be the key on ticks, and then this is the record. Okay, you could also drop index by doing drop index and then ticks pk.